Hello friends, welcome back. In the last lecture we introduced the concept of system engineering and the basic principles of system, what is the basic definition of system, how the system engineering evolved over a period of time, what is the importance of using system engineering in various applications, and what are the complexities involved in designing system for various complex systems. So today we will discuss a little bit more about system engineering, some of the basic principles before we really get into the actual design of engineering systems. So this lecture is divided into two parts. In the first part I will be talking about the classification of systems, basically the natural systems and artificial or man-made systems. Then we will talk about the engineering system examples, when do we need really to use the system engineering, and what are the system dimensions, basically what kind of social and technical dimensions are there for the engineering systems, and then we will talk about the system design hierarchy and then the role of system engineers, how system engineers play a vital role in design, development and execution of engineering systems. So let us look at the classification of systems. As we explained in the last class, we found that there are various kinds of systems. There are man-made systems and there are natural systems. So we can basically divide these systems into two classes. One is the natural systems and the other one is the artificial systems. As you know, natural systems are existing in the nature. So human body is a system, ecosystem is there, then we have the systems of planets and other celestial bodies. So these are the natural systems, and there are complex natural systems, which is a human body is an example where the complexity of the system is still not understood fully. So those are the examples for a natural system, where some of them are very simple but some of them are very complex, which is beyond our analysis at this stage. Then we have the artificial systems, which are basically man-made. So in man-made system we can classify them into many classes depending on the complexity and human involvement. As you can see in this picture, there are artificial systems with complex behavior but very simple structure, and we have artificial systems with complex behavior and structure. So there may be complex behavior as well as the complex structure for the artificial systems, but then we have systems with human intervention or human behavior, like artificial complex system with complex technical but simpler human structure. Then we have artificial complex system with complex human but simpler technical structure, and artificial system with technical and human structural complexity. So there are, depending on the system type, we can actually find whether this can actually classify them whether they are complex in human behavior or complex in technology or the technical behavior. For example, if you take the operation of a missile system, it is more of a complex human behavior, and when you take the design of a missile system, it is more of complex technical behavior. So depending on the context in which we use the system engineering, we can actually divide them into human behavior system with complex human behavior or complex technical behavior. So man-made natural system or components also may include in these systems, because there may be some natural subsystem which is part of the man-made systems. This is the basic classification of systems. Let us take few examples for these systems and then try to understand what are the subsystems involved and how they have become part of a larger system or a subsystem of some other system. Take for example spacecraft as a system. As all of you know, it can be considered as a system composed of a variety of subsystems. So every spacecraft has got many subsystems, and this spacecraft architecture, it is well defined, because there is a well defined structure for the aircraft architecture, and the subsystem are in turn composed of very smaller subsystems. For example, if you take the communication subsystem or the payload system of a spacecraft, as you can see, communication is a payload in a spacecraft, and we can consider this as a subsystem of the spacecraft. As you can see here, there are many other systems part of the payload. You can see that antenna is a part of the communication payload, amplification, modulation, demodulation, routing, encryption, decryption, filters, multiplexers, this all becomes part of the subsystem of the spacecraft. Similarly, we have the spacecraft bus, where the attitude determination and control is there, command and data handling is there, payload processing is there, then power, propulsion, software, structures, telemetry, thermal systems. So these are all becomes part of the main system. So if you take spacecraft as a system, then you can find these are as the subsystem of the spacecraft. But if you take the space system as a whole system, then you will find that the spacecraft is a part of a larger system, which is the space system. You will have many spacecraft in the space system, which is the other spacecraft in the constellation. Then you have the different segments for the space system, like you have the ground segment, then you have the space segment, then you have the launch segment. So these all becomes a subsystem, main system of the space system. Though spacecraft can be considered as a system by itself, when we define the space system, then the spacecraft becomes a subsystem of the main space system. Thus any system can be considered as a subsystem of a larger system, or it can be considered as a system by its own merits. So it depends on how you actually define the system and what actually you are going to design. So depending on that, we need to define what is that particular system and what are the subsystems of the main system, and then how do you define the boundary of the system and the subsystems. As you can see here, this actually shows the space system, where there is a launch segment, there is a space segment, and there is a ground segment, which are all part of the main space system. This figure again shows another diagram which actually shows the product development system for Ford Motor Company. We will not go into the details of this figure now, because we will be discussing it in the later stage when we discuss about the product development process or the system development process. We will discuss about it in detail, but it actually shows that how from the initial customer requirements the customer satisfaction is achieved through various processes, and how it passes through different stages of design, fabrication, testing, integration, and then validation, and then to reach the customer. So this again, the development itself becomes a part of a major system or the product development system. We will discuss this detail at a later stage. This is another example for the system, complex system, man-made system, which is the air defense system. As you can see that air defense system has got various subsystems. Something can be in the air, something can be on the ground, and something can be completely controlled by the man, or completely automated with different sensors and signal processors kept at different locations. As you can see, there are radar sites which actually used to find out the locations of the aircrafts. Then there are early warning and control systems, which actually consist of many aircraft and other sensor suites. Then we have the traffic control, air traffic control center, which actually controls the movement of air traffic. Then you have these interceptor bases where the air defense systems are placed, from where they can actually take off and then carry out the missions. Then there are civil defense applications for this particular system. So civil defense centers will be sending information to the main database center or the control center. Then we have the ammunition systems at various locations. Then there are radio sites for transmission of signals. And then we have all those base centers which actually coordinates the activities of various centers as part of this system. So as you can see, it's a fairly complex system with various subsystems and a lot of interaction between these systems, and therefore the system engineering concept is well suited for this kind of a complex man-made system. This one we discussed in the previous class about the Atlas project. As you can see, there were 18,000 scientists and 17 contractors with 200 subcontractors and 200,000 suppliers, and the whole process coordinated by Ramo Woodridge Corporation. So again, you can see that there were 200,000 suppliers. So you can see the complexity of human involvement in this particular project. Apart from the technical complexity of designing the missile, there is actually a larger complex human behavior involved in this system, and therefore we need to look at the human interaction and human behavioral aspects in the design of systems. These are the key aspects of the Atlas project. So this actually was the one of the projects which firmly established the systems engineering approach to management. It identified the key challenge early in the system, that what are the key challenges when it is re-entering the atmosphere, what are the challenges. So all those things were analyzed initially itself, and then the system design process proceeded. As you can see here, this figure shows the interaction between various entities in this particular project, As you can see, the US Air Force is one agency which is the customer in this case, and the RW Corporation is the agency which actually coordinated the whole design process. You can see there were a lot of interaction between the customer and the contractor at different stages, and this military considerations and contractual control were actually coordinated by the RW Corporation with what are the requirements of Army and how do they actually include all those requirements into the system design. And then there were many other subsystems like propulsion system, guidance system and control system, and then there were many subcontracts which are designing, developing and supplying some of the components and the system for this. So you can see there is a very good hierarchy of information flow as well as the assignment of task and responsibilities, and this actually calls for the principles of system engineering, and that is why this was one of the projects which firmly established the principles of system engineering approach to management of large scale engineering systems. So we saw that there are different kinds of systems and there are different kinds of complexities in the system, but then we need to find out when do we need to really apply the system engineering concept, whether all the projects are good candidates for system engineering or there are projects which actually does not warrant the need for a system engineering concept. So how do we decide this based on our approach to the project or based on our understanding of the project? We discussed about some of the failures in the previous class, system engineering failures in the previous class, where actually we discussed about the airbag system failure for passenger cars, and we found that there was a failure in the requirement analysis of the project. There was a failure in Pathfinder, which is again a space system where the communication failed in the Pathfinder. This was because of the interface design failure, and again the Ariane 5 launch vehicle failure we discussed. These are all various examples for system failure and whether they are the candidates for the application of engineering system design. If you look at this one, we need to find out the real causes of system failures to see what actually really happened in the system or what actually caused the failure of the system. Now this discussion point for you, you can actually find out from the literature or through discussion with your friends or your colleagues what actually happened in our GSLV failure. So we know that our geosynchronous launch vehicle failed recently, and there were many accounts for the failure of the system. So probably you can identify whether there was a system failure or it was a component failure. So probably we should be able to distinguish between these two, what actually happened, whether it's there was a failure in the whole system or the process of development of the system, or there was a component failure which actually more of an engineering failure which actually failed to meet the desired design requirements of that particular component. When you analyze this kind of failures, then you will know that whether it was a problem with the technical design of the system or it was a problem with the whole system design. So based on that we will be able to tell, okay, oh, this was a failure in the system engineering, and therefore we need to look at the process and procedures we followed for engineering the system, and accordingly we need to go ahead with the design of the system or apply the principles of system design. So let us look at what are the criteria when we decide to take the system engineering principle for a particular project. The characteristics of a system whose development, test and application require the practice of system engineering, that the system is an engineered product and hence satisfies a specified need. So that is one of the basic requirement. It is an engineered product and hence satisfies a specific need. Most of the systems actually satisfy this requirement. The system consists of diverse components that have intricate relationships with one another and hence is multidisciplinary and relatively complex. This is one of the most important aspects we need to look at. What are the different components and different systems or subsystems which comes as part of this one? What are the discipline or the technology domains we need to have to achieve the target or achieve the function of the system? So once we know that there are multiple domain expertise requirement and multiple technology requirements and there are a lot of interaction between these different domains, then it will be a very good candidate for system engineering, because multi-system or multi-domain interactions cannot be normally captured in the normal design process, and therefore we need to try to incorporate these factors into the design, or we have to take into account these factors when we consider the system design, and then we need to make sure that we apply the system design principles to such designs. Then another factor is that the system uses advanced technologies that are central to the performance of its primary functions, and there are advanced technologies which are not well proven at this stage, or it is still in the development stage. There are advanced technologies, then probably that is a very good case for system development, because system development actually system development principle basically takes care of the modeling, simulation, verification and validation of different technologies before we really implement those technologies into the system. So if any system which actually satisfies these three conditions, that the system is an engineered product and has a particular specified need, and it actually warrants the use of multiple disciplines as well as technologies, and there are newer or advanced technologies which are being used in any system, then such systems are a good candidate for application of engineering system principles. Some of the examples for such systems are the satellites, man-made satellites, aircraft, auto assembly plant, railway reservation system. So these are all some of the system or engineering system, man-made systems, where we can really use the principles of engineering system design to achieve the desired goals from the system, because they are all satisfy these conditions. There are multi-domain expertise needed. There are a lot of interactions between different domains and different subsystems, and there are advanced technologies used. For example, if you take the railway reservation system, which is one of the best online systems we have for booking of railway tickets, you know that there are multiple subsystems. There are customers, there are booking agents, there are railway station booking facilities, there are centralized servers, and there are payment agencies. All these are interacting with the main system, and they are using the latest technologies of communication and networking as well as data analysis and data processing. So that becomes a very good candidate for applying the principles of system engineering when we develop systems like this, systems of complexity like this. So in the previous class, the system engineering, which actually integrates all the disciplines and specialty groups into a team effort, forming a structured development process that proceeds from concept to production to operation. So if you apply these principles of system engineering, we can actually have a structured design process which actually will start with the development process and proceeds from concept to production to operation of the system, and it considers both the business and the technical needs of all customers with the goal of providing a quality product that meets the user needs. Okay, so this is again a discussion point for you. We discussed about the system engineering in detail. So what actually is system engineering, and when do we use the system engineering principles, what are the basic requirement of applying system engineering. So probably you can have a discussion, what distinguishes system engineering from the normal or the conventional engineering, what are the factors which actually distinguishes from system engineer, how a system engineer is different from a conventional engineer or a domain expert. So this will actually help you to understand the system engineering concept in a better way, and appreciate the importance of system engineering in developing complex engineering systems. We discussed about the system, and then as I mentioned, the system has got a technical component as well as a human component, because there are complex human systems and complex technical systems. So let us look at what are the technical dimensions of the system. As you can see, there are 6 levels of technical dimension for any engineering system. So we will start from the highest level. It is basically the physical environment of the world where actually the system operates. So we call it as the system context. So every system will be operating in a particular environment. So that environment becomes one of the dimensions of the system, because all these dimensions are important in system development, because all these dimensions have impact on the system, or the system can be impacted by those factors. So if you look at the highest one, then it can be a physical environment of the world, and then we can have different levels. If I start from the lowest level, that is a 0, that becomes the parts or lines of code of a system. So you will be having very small components which are off the shelf or which does not require any specific design, like your nuts, bolts and other kinds of screws and small fasteners. These are all becomes parts or small parts or the 0th dimension of an engineering system. If you take the software, then the lines or code becomes the 0th dimension of this technical dimension. Then the next level is the components or major software units. So if you have main components of the system, that becomes the first level dimension or the major software units in the case of software. The third level is the major subsystems or subassemblies. So you will be having many subsystems or subassemblies in a system, that becomes the third level of system. But in the case of software, then the software becomes the next level, where you have subgroups or the particular group software which actually carry out a specific task. Then the next level is the larger system, which is an aircraft. If you take the space system or air transportation as a main system, then aircraft becomes the next level of component or next level dimension here, or any system related to that. Then the higher level is the air transportation system or the air defense system. So if you consider that as a whole system, then air transportation or air defense becomes a major system, and the highest level is the, as I mentioned, it is the physical environment or the world in which it operates. So these are the 6 technical dimensions of an engineering system, and all these technical dimension has got impact on the system development. So every system can be impacted by these dimensions, and therefore we need to make sure that we take into account all these parameters into consideration when we design our system. So that is about the technical dimensions. Let us look at the social dimension. So every system has got the social dimensions, because it has some social impact, because the human is involved and it is mainly designed for human use, and therefore there is a human intervention or human impact on the system, and that is why we have the social dimension for the system. Again, we can have 6 levels of social dimensions. So the highest level again is the society, nations or communities where the system is being used. So depending on the country or depending on the society where it is being implemented, we can say that becomes the highest level of social dimension for the engineering system. Then the lowest level is of course the individuals who actually directly interact with the system or directly involved in the design, development, use or maintenance, whatever way he interacts with the system, that becomes the 0th level dimension of the engineering system. Then there are working groups or teams, either development teams or the operation teams or maintenance teams. They all becomes the next level of social dimension. Then the organization units, where the particular organization where they are developing, there will be design team, there will be fabrication team, there will be machine maintenance team. So they all becomes the 3rd level of dimension, which is the organizational units. Then single organizations are the next level, where a larger organization like DRDO becomes a single organization with many labs across the country. So each lab becomes a single organization, which is the 4th level dimension. Then there are extended multi-organization enterprises, including partners and suppliers. So this actually a group of suppliers, consumers and subcontractors. So they all become the 5th level of extended multi-organization. So if a company is developing a particular system, then there are many suppliers, quality assurance teams, there are organizations which monitor the quality of the system, there are organizations which actually is going to finally use it, they are also part of the system. So like that, there are extended multi organizations which actually becomes part of the 5th level of social dimension, and the last one is the society, as I mentioned, where actually we are going to use the system. That becomes the 5th level of the society or social dimension. So as you can see, there are technical and social dimension for an engineering system, and therefore we need to look into the aspect of the social aspect as well as the technical aspect of the system design when we start the design and development of an engineering system, which is finally going to be used by the customers, where there are a lot of human interaction as well as there are technical complexities. So we discussed about the different dimensions of the system, and I told you that there are different technical dimensions for the system. So you can see that, as I mentioned, there are lower level parts or components, which actually becomes the 0th level system dimension. Then there are sub components where actually the signal amplifier, cathode ray tubes or gear trains or valves or nozzles becomes the sub components. Then we have the components like signal receivers, data displays, power transfer, material reactors, thrust generators, etc. Then we have the subsystems where signal networks, database, material preparation, engines, etc. are being used for developing the final system. And you can say that these are the communication system can be a system on its own merits. Then there are information systems, material processing system, aerospace system. So these are all the top level systems, and of course when you use these systems for another system, then this becomes subsystems of the another major system, like air defense system. If you take as a main system, then this communication, information, material processing, all this becomes the subsystem of the main system. So that was about the system in general. Then we need to see, okay, who are the people who design it and what actually they do. So these people who are actually responsible for design, development and integration and verification, validation of engineering systems are known as system engineers. They are different from the engineers or the domain experts like mechanical engineer or electrical engineer or an electronics engineer. System engineers are not exactly the domain experts, but they are more like people who actually see the big picture and try to integrate many things into a single piece. So they will be having the larger picture of the system, and they know what can go wrong, what are the issues coming up. So they will actually do the troubleshooting and then make sure that the system development process takes place in a structured manner without any problems. So the system engineers are those who design the overall architecture, but they are not the people who really design the components. Component design is basically done by the domain experts or the engineers or mechanical engineers or electrical engineers. They prioritize the system requirements. So there are different requirements for the system. Those who are designing the component may not be knowing what are the actual requirements of the original system which the component is a part. So the system engineers are the people who actually prioritize the system requirements and design the components or identify the components or the requirements of the components and then pass it to the design engineers. And the system engineers, people who decide on the risks to be undertaken. There may be many inherent risks in developing a system, because every system is a totally new system and there are different technologies employed, and therefore there are risks involved in designing the system. So these are the people actually who will analyze the risk in designing the system or using a particular technology for the system, and they try to understand the risk involved. They try to ensure that the risk what they are taking is it's a calculated risk, or it's a risk understood by the design team, so that they are prepared to make the changes whenever it is necessary. And they decide on the risk avoidance strategies also. So when they identify a risk, they will try to see if the risk can be avoided, and so they built in functions and procedures to avoid the risk. And then they decide on how the system performance and system affordability may be achieved. So affordability is another important aspect. So they are the people who can actually look at the performance requirement from the customer and the business aspect of the system. They need to have a proper balance between these two. So they analyze the system performance and system affordability, and then go ahead with choosing particular technology or components. They guide the system development purely on their knowledge of the system. So they are the people who really know the complete system. They know what actually is expected from the system, what are the subsystems going to come in the picture, and what are the types of interaction going to happen between the system. So they guide the system development based on the knowledge what they have for the particular system, and they decide how to tackle unanticipated problems. So it is very common that there will be a lot of problems coming up in the development process. So they are the people who actually tackle all these anticipated problems and then take the design forward or the system development forward to ensure that it is delivered in time and with desired performance requirements. So what are the knowledge domains where the system engineer operates. As you know, as I mentioned in the previous slide, that their responsibilities are much more than the design of components. So they are the people who actually manage the whole design process. So what are the domain knowledges or domain areas where the system engineers operate? As you can see in this picture, the parts and subcomponents are the duty of a design specialist. So the system engineers will not come into the design of parts or subcomponents. So they will just give the specification for these components and parts to a design specialist. Then the design specialist will design the component, he will select the material, he will select the software or whatever sub system required for that particular design. They will identify those requirements and then develop the parts or subcomponents and pass it to the next level where the components are assembled or they are integrated into a subsystem. Then there are subsystems and systems which are actually the domains of systems engineer. So the system engineer is the person who actually do the integration of systems, or they are directly involved in getting these components into subsystems and integrating them into the major system. So the domain of the system engineer actually is in this area, where you can see that subsystems and to some extent the component level integration are part of the system engineer responsibility, and the design of parts and subcomponents are purely done by design experts. So they are the people who are from the electrical engineering domain or mechanical engineering domain or with electronics or software specialists who actually do this specialization in particular component development. So there will be design teams, separate design teams who will be charged with the designing of these components, and finally it will go to the system engineer, where the system engineer will integrate them to sub-assemblies, do the testing, verification and all the required procedures to ensure that these components and subsystems are performing to the desired requirements, and then they go for integration to the system level, and finally the system will be delivered to the customer by the system engineers. So there is a clear role for the system engineers who actually responsible for the delivery of the system, and therefore they have that big picture what is actually expected from the system, and accordingly they will work in order to make sure that all these components and system subcomponents designed by the specialist are meeting the requirement of the system. And then, as you know, these are the responsibilities of the system engineer. So a good system engineer need to have some characteristics which are actually needed for managing the whole project. So these are the people who actually enjoy learning new things and solving problems. So every time there will be, every project is a challenge, every project is new to the system engineer, and they really enjoy learning new things and solve problems, and they like challenges. So these are the people who really like challenges to take and then design something new and try them, and then chances of failure they will try to make sure that these systems, these are the new challenges, and they keep on doing these things because they love taking challenges. They are skeptical of unproven assertions. So whenever there is an unproven assertion, then they will question that particular assertion and then keep on challenging that one to make sure that they understand the whole concept, and they are working with complete knowledge of the whole process or the system. They are open-minded to new ideas. So every time it's need to be have new ideas and new concepts for developing systems. So they are always open to new ideas, and they have a solid background in science and engineering. That is important. So it's not that they don't know engineering just because they don't do the real design of components or subcomponents. That does not mean that they are not engineers or scientists. They have a very good solid background in science and engineering, which actually helps them to understand all the complexities of the system and identify the components and parts for the system. They have demonstrated technical achievement in a specialty way. So they have, because of this particular job role, they have demonstrated their technical achievement in a specialty way, that is system engineers. So like a managerial capability or problem solving skills or identifying the risk involved and then trying to find out new ways of avoiding these risks. So these are the some expertise they develop during their career, and they are good in such activities, and that's why they are a system engineers. So they have demonstrated the technical achievement in a specialty way. they are knowledgeable in several engineering areas. So that is another important aspect. One problem with our engineers are that a mechanical engineer is a pure mechanical engineer. It is difficult for him to communicate with an electronics engineer or an electrical engineer because they talk in different terms, or the terminology an electronics engineer uses may not be fully understood by a mechanical engineer. But system engineers are not that kind of engineers. They actually understand different streams. So they would have good knowledge about mechanical engineering concept, electrical engineering concepts, communication and software, though they are not the real experts in that area, but they understand most of the things what is happening in these areas, and they are very comfortable in dealing with a mechanical engineer or an electric engineer without any problem. So this is one of the important quality of a system engineer. They can actually have multiple domain knowledge, and this actually helps them to understand various procedures and processes in system design. They always pick up new ideas and information very quickly. So that is again important, because they are these guys are smart enough to understand the new ideas and new concepts very fast and implement it in system design. They have good interpersonal and communication skills. As I mentioned, there are a lot of manpower involvement in the design, development and integration, testing and all those aspects of system engineering. So these people are very good in interpersonal relationships and communication skills. So they can communicate well with others, their subordinates as well as their seniors and their colleagues. They can actually have a good relationship so that everything goes smoothly within the organization without any problem. So these are the good characteristics of a successful system engineer. Then what actually system engineers need to do? So system engineers are as problem solvers. So these people are really into solving problems almost every day. So every problem has three components. As you can see, there is an undesirable initial stage, a desirable goal stage and obstacles that prevent the transformation from undesirable to desirable state. So these are the three components of a design problem, and every engineer will be trying to solve these to get a solution. So as a system engineer, as a problem solver, will look at the problem, what is the undesirable state and what is the desirable state, and what are the things which actually prevent from reaching that desirable state, and then try to find a way to reach that desirable state. So that is the role as a system engineer. And the characteristics of good problem solvers are they are intelligent and creative. So creative thinking is an important quality of a good problem solver. So he need to look at the problem in an intelligent and a creative way, and try to see whether he can adapt an existing technology, or he has to look for a new technology, or he can try to find a totally new or innovative way to solve that problem. They are good decision makers. So their decision making behavior is very good. They recognize the dependencies very fast. They estimate the importance and urgency of the particular problem, and their continuity, and they are very flexible. They maintain the continuity with the problem and flexible enough to make changes whenever it is needed, and they are very good in accepting failures. So there is no fear of failure for these problem solvers, because always there is the risk of failure, and it is which part and parcel of any problem solving. So these people are they are not worried about failures, because always they take it as a stepping stone for the success. So these are the good characteristics of problem solvers. Okay, so at this stage I would like to give you a few assignments and project work. So the first assignment for you is to identify 5 natural systems and 5 artificial systems. Decompose one of these systems into technical and human systems and identify the levels of interaction. So as I mentioned, there are many natural and artificial systems. So you identify a few of these systems and take one system, any one system, and then decompose into technical and human system, and try to understand the interaction between these systems. So there will be always interaction between the human system and the technical system. Try to identify what are the types of interaction taking place between these systems. So you can, as I gave you many examples for like a railway reservation system, or a satellite system, or a missile system. So, you take any artificial system which is of which you find is interesting, try to analyze this system and then get the technical and social dimension or human dimensions and interaction between human and the technical system. This is the first assignment, and I would like to give you a group work. Of course, if group work is not possible, you can take it as a individual assignment. You take from the history of industrial disasters, identify one case study for system failure. So, which I explained many system failure case studies. So, I request you to consider one system failure which is not discussed in this these lectures. So, take one system failure, identify the causes for the failure and make a presentation in the case by highlighting the factors like the system details, failure modes, failure analysis, root cause and the proposed solutions. So, these are the things what you need to do with this particular case study. So, once you go through this case study, you will have a lot of information where actually it went wrong, whether it was a real system failure or it was a component failure, and if that was a system failure, what actually could have been done to rectify it, or from the history if it is available, what actually was done to solve that particular problem in rectifying the mistake of that particular system. So, make a good presentation and then you can send it to me, we will discuss it if you want to do so. There are multiple softwares available for engineering system design. So, one of these software is Core. There is another software called SysML. This Core is available commercially. It is from Vitech Corporation, www.vitechcorp.com. IIT Madras is a partner in Vitech's university education program. So, our students are allowed to download the student edition and use it for their assignments and projects. So, if you want to use this particular software, you can send me an email. I will send you the password and the procedure to download the software. You can use the software for your educational purpose and you can use for your assignments and projects. I will be giving you many more projects and assignments which require this kind of softwares. I will be giving you a lecture on how to use these softwares at a later stage. So, till then you can actually refer to the manual of this particular software about using the Vitech's Core software. As I mentioned, there is another software also, it is known as SysML, SYSML. So, this also can be downloaded and can be used for system engineering applications. Okay, to summarize this lecture, so we identified that the system is a set of interrelated components working together to provide a objective or a goal for the project, and the system engineering is the function of guiding the engineering of a complex system. So, system engineering is nothing but how do you guide the design and development of a complex engineering system. System engineering is a powerful discipline requiring a multidisciplinary knowledge, integrating diverse system elements and the ability to perform approximate calculations of complex phenomena, thereby providing sanity checks and skeptical positive thinking for prudent risk taking. Okay, so that actually ends the this lecture. So, from next lecture onwards, we will be looking more into the complete design or development of system from a system engineering perspective. I will take you through some of those methods and procedures to design engineering systems. So, till then, goodbye.